Good afternoon, everyone. Thank you for joining us on our webinar here on aerosol monitoring. My name is Tom Douglas. I'm with RACO. And joining us today also is Scott Norman with TSI, and he'll be leading our webinar today. Scott is the product specialist for the health and safety product line for TSI. He has over 20 years experience in the industry. He's a certified industrial hygienist and also a certified safety professional. So we thank Scott for his time and appreciate him sharing a little bit of his knowledge with us. A couple housekeeping issues. We will be recording this webinar, so if you missed part of it or wanted to share it with some of your coworkers, that will be available to you if you go to raco.com and our training page. Second, if you have questions during the presentation, we have a lot of people joining us, and probably the best way to do so is there is a chat box on the bottom right-hand corner of the webinar. Please enter any questions in there you have throughout the presentation, and we will address them at the end. So without further ado, I'm going to pass this over to Scott. Scott, thanks again for your time. And
okay, thanks. All right. I don't do a lot of webinars, so I'm talking to a blank room, which is interesting here. So start typing text messages in if you can't hear me or something's wrong. So photometer basics. Today we're going to cover a little bit about how...
the broadcast is now starting. All attendees are in listen-only mode.
We're going to cover how light scattering photometers work to measure aerosol mass. As Tom mentioned, I'm the product specialist with TSI. By product specialist, I'm in the marketing group, and I help with rollout of our new instruments, and I'm the application support for how our instruments are used. So I'm the health and safety product line, and I come from the field of about 20 years of experience in health and safety. And it's funny, a lot of my experience has been with semiconductor and clean room, which is the last place you need a photometer for measuring dust. So it's kind of funny how big picture where your career brings you. Okay, so let's see if the slide advances here. All right, as an overview, we're going to start talking a little bit about some basic physics, so very basic aerosol physics. I can't cover a lot of it here. A lot of it goes way over my head. There's a lot of PhDs in the building here at TSI that can explain it better than I, but I'll give you a simple overview of how some of the aerosol physics works with respect to how our instruments use that for measuring. We'll talk about how the light scattering photometer works, and then get into the strengths and limitations of these instruments and why they're used, and then have some field examples, of customer examples of what's been successful, some people in the past. And we do have time at the end to do some question and answers, so we'll get most of your questions answered by the time we wrap up here. So industrial hygiene exposure monitoring is really trying to find out what the worker's being exposed to. And a big part of that exposure assessment is airborne. So what are they breathing? What's the inhalation hazard? There's obviously gases, vapors with certain chemical products, but fumes, dust, mist, the aerosols are what we're going to talk about today. So I'm going to use the term aerosol. That's what research scientists usually use. And an aerosol can apply to a fume, a mist, a smoke, as well as dust. Or sometimes if we say dust, we limit ourselves, kind of limit our vision of the piece of rock that's been ground up. But an aerosol can be more than just dust. It can also be fume, mist, smoke. So let's think in terms of aerosols. And typical industrial hygiene is you're measuring this on a filter with a sample pump, send it into a lab for gravitational analysis. And that's not going to go away. So what we're going to talk about today is how the photometric instrument can supplement this process and help with some additional data that can maybe make some decisions a little easier. The more data you have, the better decisions you can make for protecting worker health. So to get into some of the characteristics of aerosols here, aerosols have a lot of different characteristics that affect the way the light scattering instruments will see them and measure them. So the size, the shape, the density of the aerosols are really the most important part. So size is really often defined in diameter, aerosol diameter, and it's usually the average of the particle size. So not very many aerosols are actual spheres. A liquid aerosol is going to be a sphere because the contraction forces of the water molecule. But if you look in the upper right-hand corner, there's some different shapes of granules there that, the aerosol may not be a perfect sphere, but the way it's measured is kind of calculated as a diameter as a perfect sphere. The shape, there's different shapes as we see in the picture there that can affect the way the instrument measures. A fiber is going to measure a little differently than something that's square or a cube, kind of like a crystalline structure. So they'll all affect the way the instrument sees these scattering of light. The density of the aerosol is very important for the photometric measurement. So the instrument is going to be calibrated to an aerosol of a known density, and when the aerosol properties change and that density changes, a different type of aerosol, that mass measurement is going to be affected and start to shift, change a little bit. So we're really calibrated to an aerosol concentration of a known density. At the bottom there's a picture of some different colored aerosols. Color could have some effect as well. Obviously, if you're measuring light scattering from a white aerosol, it may scatter a little differently than a black aerosol. I don't have data around that, but I'm just thinking there's probably some elements there. So there's numerous textbooks, and people who study this, there's a lot of physics behind the properties of aerosols, and obviously I don't understand all of it. I'm not going to cover all of it today, but I bring this up with appreciation. There's been a lot of studies done on the health effects of aerosols on the human, on lungs, and how the instruments measure those and different ways of measuring those. So there's a lot behind this, and you start looking into some research papers. A lot of those research papers reference dozens of other studies. So when we talk aerosol, a lot of times size is where the discussion starts. The size is very important when we characterize the health risk of an aerosol, and because the size determines where the aerosol is going to deposit in the lung. A lot of what we're talking about is really small. A grain of sand on the beach is really huge when we talk to the aerosol language. Those are the big boulders. Those are 90 microns across. We often refer to aerosol size by PM, particulate matter. So on this slide you'll see PM2.5, which is 2.5 microns in diameter. And this slide tries to illustrate how much smaller those are than a PM10, which is 10 microns in diameter, compared to the diameter of a typical human hair, 50 to 70 microns, and a grain of sand, which is 90 microns. So we can see things without magnification with our eyes. It's things that are probably 50 to 100 microns we can easily see. So stuff smaller than that we can't see is what we really want to be measuring with these instruments, because those are the things we're not aware of. We can't see them, and those are the ones that are going to penetrate deeper into the lungs to cause the damage in the air exchange regions of the lungs. Here's a slide illustrating the respiratory tract and where those different size aerosols deposit. So if you've done anything with aerosols before, or dust, and some presentations, you've probably seen something like this. The large particles, stuff greater than PM10, so what's called total inhalable, is usually 100 microns down to 10 microns, and that will stop in your nose and your mouth. The way your nose and mouth is shaped, when you breathe these big particles in, they're going to stick to the sides of your nose, the sides of your mouth. They get hung up in the hairs, and then you mucous membranes. You blow your nose at the end of the night, and that's the stuff that kind of comes out. Those are the big particles. It's the smaller stuff, less than PM10, the 10 micron down to 2.5 microns, that get into the lung cavities, into the trachea area. They travel deeper into the lungs to deposit there and cause other health effects. The smaller ones, smaller than 2.5, smaller than 4 microns, which is respirable size, those are the size that get deep into the alveolar region, which is the air exchange area of the lungs. So where that oxygen exchange is actually happening. The small particles that get down there start to clog up those mechanisms of the air exchange, and that's where the emphysema starts. That's where the lung tissue gets scarred. That's where the breathing starts to be impacted. So that's our concern with some particles there, especially the silica causes certain types of damage. Asbestos causes a certain type of damage to the lungs. And a lot of that's beyond the scope of this presentation, but I want you to understand kind of the size and where they're coming from, and why it's important to look at these small sizes. And it kind of comes back around to some of the properties here. So there's aerosol properties. Different aerosols have different properties that affect photometric light scattering measurements. So all aerosols are going to, in some way or another, absorb light or reflect light and or refract and diffract it. And then light passing through an aerosol concentration is going to be affected by the properties of that aerosol. So if you think of even driving your car at night and it's raining or foggy and cars coming at you, those lights from the oncoming headlights a long ways away, you're not going to see them as brightly if it's foggy or if it's raining or snowing, because there's aerosol in the air absorbing some of that light coming to you. So these are some of the properties that affect how a light scattering instrument works. to measure the aerosol mass. So this is a schematic of a light scattering photometer. I'm using one of our dust tracks here as a reference. This is the kind of simplified side view. It shows where the aerosol comes in the top, and we separate off what's called sheath air that goes through a HEPA filter, and what that does is create a tunnel of clean air that carries the dirty air through the optics chamber. So the aerosol-laden air goes through straight down to the middle, and sheath air surrounds it. It helps carry it through the optics without clogging the optics up as much as if there were no sheath air. So it's a function to help do a larger, greater mass concentration without contaminating the instrument. The instrument should last longer without needing to be cleaned. The air comes through the optics chamber where there's a light source. It's either laser diode, some kind of wavelength. There's focusing optics. That light will illuminate that fog of aerosol, and the light will scatter off the mirror and be focused to a photodetector. So the photodetector will read those light flashes and measure how bright it is and send a reading to the instrument, which then displays what that mass is. With our dust tracks, we also have added a gravimetric filter, so there is a cassette. You can put a filter media in and take a parallel sample. Along with when you're doing aerosol mass measurements, you can also get a filter sample in there to send into a lab for analysis. And then it comes out through the pump. So that's kind of the basics of how this works. And as we're looking at that, people think, well, how does it count the particles that fast? Well, a photometer really doesn't count the particles as much as it measures the light scattering. So we're measuring scattered light, we're not counting particles. A particle counting, if we compare it to like driving a car and it's raining, you can count the number of drops on the windshield. That's kind of what an optical particle counter does. So an OPC or an optical particle counter will count the number of raindrops or the number of snowflakes that would hit your windshield. And that's going to work fine in certain concentration levels and certain size levels, lower concentrations. A condensation particle counter works in a very similar way. It's going to count the actual number of flashes of how many particles are in the air. So that's optical particle counting. That's condensation particle counting. A little different than photometric light scattering. So what the photometer does, photometric light scattering, is we're really looking at the fog. So this was explained to me and it made a little sense. I tried to explain it this way, that we're not looking at an individual particle, but we're looking at the light scattered by the group of particles, or the fog. So think of driving the car at night in a fog. When you turn the lights on, light scatters back at you, you see the bright fog in the headlights. And the thicker the fog, the brighter it is. That's kind of what the photometer sees when the aerosol is coming through the photometric chamber. The brighter the fog of aerosol, the heavier the concentration is, and it compares that to a known aerosol that's been calibrated to, and it gives a measurement. So we're measuring the fog, we're measuring the aerosols as a group, not just individual particles. And we compare that to a known size. So the instrument has been calibrated to a test aerosol, and I had a hard time getting my head around this until I explained to someone, well, it'd be like different sized balls. And so if we think of the test aerosol as a golf ball, and we can picture how heavy a golf ball is, the density of a golf ball, how big it is, how shiny it is. We know a lot about the golf ball. Well, the instrument will see those golf balls, and it doesn't count them. But if we were to spill a whole bunch of golf balls on the road, the instrument sees light scattered from a mass of golf balls. It's going to know that's going to weigh about this much. Now, if all of a sudden we spill a bucket of ping pong balls, now there's an aerosol of a different density. Ping pong balls are lighter, a little different shape, a little different size. They obviously don't weigh as much. So if the instrument doesn't know they are not golf balls, it's going to send the same signal thinking it's golf balls. That's where these instruments can vary a little bit. That it's precise to the number of the mass of what it's measuring for light scattering, but it's not accurate unless it's calibrated to the specific aerosol we're seeing. So if it knows it's seeing golf balls and it's measuring golf balls, we're accurate. If all of a sudden we mix ping pong balls in or tennis balls, the accuracy is going to be off. Your read is going to be shifted a little bit because it's not directly calibrated to that aerosol. So that's where a calibration factor comes into play. So an instrument is calibrated to a test dust, and we use what's called Arizona road dust. It's typical of just dust you'd find on a gravel road. It's typical of outdoor ground-up rocks. And that's what the instrument sees as the baseline. The baseline is the test aerosol. If we expose that instrument to a different kind of aerosol, the readings are going to be a little bit different than the bench line because now there's a different density, different properties of that aerosol. We've seen some studies, and we've linked to this with some application notes. Some studies have been done that shows the outdoor urban pollution, which is mainly combustion byproducts from airplanes, cars, trains, and burning fuel sources. If a calibration factor of 0.38 is used, then that photometer will read pretty close to what the actual gravimetric measurement is. So a way to determine that is doing some side-by-side sampling. If you run a photometer side-by-side in the same aerosol for the same sampling time with the gravimetric sample, you can weigh out the gravimetric reading, get the gravimetric results, look at the information on the photometer, go back and run a formula, and you can determine a calibration factor that can then be entered into that instrument. Then the instrument running next time with that calibration factor is going to get a little closer to your actual mass of that aerosol, which works fine until the aerosol changes. So if your aerosol changes throughout the course of the day, then results are going to drift a little bit because it doesn't know the aerosol's changed. That really comes down to, the photometer sees all these aerosols, all these different shapes and sizes. It measures the light scattering these particles as a group. It's going to calculate mass based on the properties of that calibration aerosol, or that test dust. But if the aerosol changes, it's not going to know the difference. So that's where this instrument has a little bit of a limitation. These aren't going to be used as reference methods for pure OSHA exposure monitoring to permissible exposure level. It's very accurate measuring an aerosol. It's very precise measuring the aerosol levels, but the accuracy is determined by how it's calibrated to the actual density and size fraction of that aerosol that's being exposed to. So that, as we're talking, there's some limitations to this. So one of those limitations is really just the calibration aerosol. So it's very precise, again, to the aerosol it's been tested to. It's accurate to that level. It's not going to work as a standalone reference method unless you verify the aerosol concentrations and done the gravimetric comparison to get those back. If the aerosol changes during your sampling time frame, then your readings are still precise to the aerosol level, but the mass may be different than what you read gravimetrically because of different density, different size, different changes in the aerosol. Humidity can have effect on photometric measurements. So we've seen studies that in some atmospheres, some aerosols are hygroscopic, and when humidity levels get 50 to 60%, they're going to grow, they're going to swell. So picture a sponge in the sink where you're washing dishes. That sponge is full of water. It's a lot heavier than a dry sponge. And aerosol, as it grows and absorbs moisture, it's going to grow in size and swell. The instrument's going to see that larger particle and assume larger mass. It's going to scatter more light. It's going to read it as a heavier particle. Your readings are going to be elevated slightly over what they probably naturally are if it was not humid. So these can be dealt with by inlet conditioners that dry the air out. And even when we do gravimetric sampling, most of the sample media gets conditioned in the lab before it's sent to us as a pre-weighed filter, and then before it's weighed for the final analysis, it gets conditioned again at a certain temperature and humidity for a certain number of hours to make sure any water that's collected out in the field has been dried back out of that filter media. So dealing with humidity is understood, and it's just something to take into effect that couldn't be interfering with the readings if we're not conditioning out the humidity ahead of time. And then optics contamination. So if this instrument is put in an area where the heavy levels of dust are being unloaded or blowing in, this optic chamber will eventually clog up. It'll eventually get plugged. The readings will start to drift. There's a zero process where you put the zero filter on there, easy enough to kind of baseline it out. Eventually it gets contaminated and needs to come in and get cleaned. So if there's an area where there's heavy dust accumulation, you really don't need a photometer to measure dust. You know the dust is there. Get rid of the big stuff, manage that. Use the dust track, use the photometer to measure areas where the aerosol is lighter, where you don't see it, where what are we being exposed to, the small stuff that could be breathed in deeply. If there are areas outside where instruments need to be, we've encouraged people to use use a PM10 impactor that's going to cut out the big stuff that will plug up the instrument. That way the small stuff still gets in, you're still getting those readings. But that is a limitation of the instruments. They will eventually load up and need to be cleaned out in high concentration atmospheres. So there are some limitations, but there are also a lot of strengths. So the benefits and strengths of using these instruments is it's a real-time measurement. When you take a gravimetric sample, you have to calibrate the pumps, you have to measure the flow rate, put the filter on, the filter's on the person during the day, that full day of sampling, post-calibrate, you use a chain of custody. There's a lot of steps to sending that information out to the lab, and then the sample goes to the lab for analysis, and it may be 4, 5, or 10 days before you get the results back. With a photometer, you have real-time results during the monitoring period. At the end of the day, you know what the total accumulation has been. So you have real-time results that can help you make some decisions on a quicker basis. You can data log this information. You have data points all day that are being recorded in the machine. You can download to a computer. You can graph those out. I'll show you in a graph in a minute here that helps point that out. It's direct reading. There's alarms that can be set. So during the course of the day, if we exceed a certain set point, the instrument can trigger an alarm telling people to either activate engineering controls, stop a certain process that may be causing the problem. Maybe it's time to put a respirator on. So we can use that real-time information to trigger alarms and help us. Again, it's information available right now. It can help us make better decisions to protect our worker health. So stepping back to gravimetric sampling, typical sample pump, there's a cassette to take an aerosol sample, some kind of particulate you clip in the worker's breathing zone. You're going to calibrate the pump, put it at a known flow rate. It's going to measure for 8 hours. Goes into the lab, gets sent back. You look at the result, and you get a number, your total mass collected of the aerosol. Now, the lab can also tell you what is in that sample. Is it lead, or is it chrome, or is it some kind of heavy metal, or some kind of other material? But really, what we're looking at is the mass. So let's say our number is 5.527 milligrams per cubic meter. That's great. That's, if we say our permissible exposure limit is 1.5 times that, or we're half of that, we're good. We'd probably take a couple other results to verify. You say we're below the level of concern, we're okay. With real-time measurements, we're still going to get the total mass 0.527. But when we're using a direct reading instrument, we can also download and graph that data in a graphic form. Now, this is simulated data. I just put this together to show a point. But let's say we had the same number, 0.527 milligrams per cubic meter, and if the green line represents our exposure limit, you say, yep, our average is below that exposure limit, but there are these 2 times during the day when our exposures were much higher. Now, our average is low, our average is safe, but is this a chemical or contaminant or some kind of process, some kind of exposure? We don't want people above the level of 1, or we don't want them above the level of 2. I mean, we may want to focus some resources on what's that person doing at those times, and maybe that's where the engineering controls are put in place, or that's when the respirator is needed. So there's some data you can get from a real-time instrument that's going to help understand what's going on in the course of the day. And that's, I think, the biggest benefit of these instruments. You get information like this to take some better information, record data, make better decisions. Another way of using these instruments is think of it as a noise meter. You'd take a noise meter to sample around a shop or different places. You could take the sample the same time every day, the same time every week, and just trend your aerosol levels over time. And as they start trending up, say, what's going on? Why is the aerosol levels increasing? So what are these aerosols used for? The real-time measurement. We have direct reading, so we can take those samples like a noise meter. We can take aerosol level samples around different sites of the plant. We can log that data and trend it and put it into a graphical form. We can use that to trigger alarms. So there's a lot of things we can do real time with that information that help us make some better decisions to protect workers. So where are they used? What are they used for? Some different dust sources. This is a variety of things I had together from another presentation. You see dust everywhere. So construction, mining, agriculture, that's the big stuff. You see that stuff blowing around. But in that dust, especially construction, the focus is silica. So PM4 respirable, there's silica dust in there at that small size fraction. Any operations with high heat, if you're welding, there's a potential to generate welding fume. Hexavalent chrome is an issue for welding on stainless steel. Foundry work, again, has an issue with silica with the sand in the molds. Even woodworking, the big part of the dust, the stuff you see, the stuff you brush off your arms, not a big deal, but if you're using high energy to grind or sand or maybe process something, anything high energy is probably making a small particulate you can't see. That's where the aerosol monitoring comes into play, to pick up that fine stuff in the air that you may not be seeing and don't even realize is there. So a couple customer examples is we have a customer that has several mines. They're surface mines for aggregate, kind of like a big gravel pit, and they've characterized the silica levels in the rock in the different parts of the country where these mines are. And they've used the AM510, and they've done a lot of side-by-side gravimetric samples with the AM510 and the photometer, and they've been able to develop a custom cal factor. So they know for mine XYZ in this part of the country, they use a certain cal factor. It's a little bit different in another part of the country, but they're able to track their silica exposure on a regular basis. So they've done monitoring with gravimetric to prove they're in compliance. That's what Aerosol buys off on. Now they use the AM510s on a regular basis to make sure those exposure levels haven't changed. Shell Oil Company in Canada had several dust tracks, and they had an issue several years ago where the oil sands are being mined. This is on the oil sand fields. There's a forest fire in a ways off. It wasn't on their property. They were concerned for their worker health based on the smoke in the air from the forest fires. So they used the dust tracks as a real-time measurement to make an hourly decision. They made decisions every hour based on what's the particulate level in the air when they need to move workers into safety away from the smoke. So there's an example where a real-time instrument was valuable. They couldn't make those decisions if they're sending samples into a lab for analysis. The EPA in Australia has several dust tracks scattered across the outback and then along the coast, and they're measuring particulate levels. The ones in the outback are using them as early warning indicators for dust storms and wildfires. And these are hooked up to solar power systems and wireless communications, so they're pretty much standalone self-powered units out in the field. Fugitive dust has become a bigger issue recently, and we've seen that with some of our sales. By fugitive dust, we mean stuff that's stirred up by human activity, so it's not coming out of the smokestack. It's stirred up by mining, agriculture, and whatever. And so companies have used these to kind of monitor fugitive emissions at the perimeter of a construction site or a work site. So here's a picture of an environmental enclosure with a dust track and several other instruments. During the construction of the Meadowlands Stadium in New Jersey, they had fence line monitoring set up. So activities on the site weren't causing, aerosol particulate dust levels of concern for the community surrounding the construction site. A similar application is underway right now. That was a big sale we had this spring. Comstock Mining is a gold mining company. They're based in Canada, but they mine around the world, and they have a new ore deposit they're going to be mining in Virginia City, Nevada. And usually gold mines are 50 miles away from the nearest road, but this one happens to be right across the street from the city limits. So it's been in the news. The community's concerned of how messy and dusty this is going to be. And the mine company's been proactive with this. They came to us. They wanted a real-time monitoring solution, and we set them up with an enclosure, the dust track, wireless cell phone, web-based communication system, so they can wirelessly monitor their dust levels all around their site, real-time, all the time. And alarms get sent when a set point is triggered. They get a text message or an email, and they can take action to stop the trucks or spray down water. So they're using this to help address community concerns before they can start causing a problem. So they're using that to be a good neighbor. They're also taking measurements out in the desert in areas they're going to mine in the future. So they're trying to get a handle on what is just the natural ambient dust levels out in the middle of the desert before they've mined there at all. There were dust tracks used during the oil spill in the Gulf of Mexico several years ago. So this was used to help quantify EPA reporting as far as particulate mass, particulate levels in the air, and then to make evaluations for protecting cleanup crew members. There is a dust track and a P track on the International Space Station, and we were in the space shuttle as well, and those were being used as early warning smoke detector. So smoke is a ultrafine particulate, so if a fire were to start, that'd be pretty bad in the space station, and P track is used as an early warning smoke detector there. The U.S. Embassy in China has a dust track that broadcasts wirelessly. China's been in the news. They get a bad rap for unhealthy air levels, and the U.S. Embassy puts out a daily air quality index based on U.S. metrics. So PM2.5 is one of the elements that are measured, PM10 as well as soot, ozone. There are like 10 constituents are measured, and so they're measuring that in real time, and they give recommendations to U.S. personnel working in China as far as what they should do to protect themselves from the air levels at the time. So this was taken back in July, which levels that day were considered unhealthy. It's interesting to note, during the Olympics, China turned off a lot of their factories burning coal, a lot of the coal power plants, and shut down a lot of transportation, help clean the air up for the Olympics. So that's both to help the athletes and just to put a better show on for the world. So once the Olympics were over, then the factories turned back on. And China has a plan to eliminate and phase out coal-powered power plants and switch over to natural gas. That should clean it up a little bit. It's interesting too, we have had some dust track sales to apartment managers in China where the air quality is so poor outside, it's actually a selling feature for the apartment that they have filtration and they have clean air inside, and they have a dust track in the lobby. They say, come and live here, we're clean inside, our air is clean here, here's the proof, here's the dust track. So this kind of summarized what we talked about. Light scattering photometers, it's a precision instrument that very accurately tracks aerosol level. It's portable, gives real-time results, direct reading results we can take action on right away. The limitations are that calibration issue with calibration dust, and that can be worked around by understanding which aerosol is and compare it to gravimetric measurement. But the benefits of that real-time information, the data logging, is really another way of having data that you don't have with gravimetric analysis. It gives you more information to do more work with and make better decisions with. And with the expansion of fugitive dust monitoring, we put enclosures in place that here's a solution now. The dust monitor can be outside 24/7 standalone, solar power, wireless communication, and really take care of itself to stream information back to your headquarters in real time so you can monitor what's going on in the field. So that wraps up the presentation part. Tom, if you want to come back in and if you want to do question and answer here.
Yeah, thanks so much, Scott. I think the very beginning part might have been cut a little bit, so I'm not sure everyone caught that. We did get a few questions that came through on the question pane, and we can address those. And if anybody else has any questions, please go ahead and type them under the questions box on the orange right-hand side of your screen. First one's asking if does the dust track have a filter that can be used to calibrate the measurements?
Does it come with a filter to calibrate? So it comes with a filter cassette, and there's just a blank screen in there just to keep big particles out of the pump. So you'd have to talk to whatever analytical lab you use, and they can sell you either the filter media to put in place, or probably just send you the whole pre-weighed filter cassettes. Our manual spells out the preferred part number. It's a 37 millimeter two-piece conductive cassette, and you put in whatever filter media you need for the analysis you're going to do.
Another question, somebody that's in construction, IH safety, mentioned that dust, particles, fumes, mists are from varied matrices and commingled with no real way to measure the percentage of each in the cloud, and asking how a photometer would be able to help that. Well,
it's going to, levels from one day to the next to be easy to track. You might not have a baseline to compare it to as far as what is the level of concern based on, what is the dust? Is it a harmful dust with toxic properties, or like a silica where there's an exposure level, or general nuisance dust? So that's where, if you get this, maybe rent an instrument and try it out and play with it, see what comes up, and you'll start finding ways you can get information from this. Be beneficial to track on a daily basis or weekly basis trends. You'll start to see, hey, we're 50% higher this week than last week. What changed in our process, and how can we affect that? If it's outside, you're probably subject as much to the what's the wind direction going on, and probably more so than what you can control. Although there are some strategies for dust control that, putting down, there's dust suppression materials and water type things, so that maybe, if it's a perimeter monitoring type thing, you'd set your own action limit of, here's the number we've been reading as a baseline. If we can only exceed twice this limit, we're going to turn the dust control on. So maybe you don't reference it back to an actual established number, but it's a number you established on the site for your activities, and you're going to kind of track yourself, measure yourself to your own number.
Another question asking about the U.S. Embassy in China is using dust track to monitor PM2.5.
Yes, they are. So,
are they? Okay.
Yep. Yeah, that was one of those slides, and they're measuring 2.5 and PM10. So both or one or the other. Anyway, that was one of those slides I did find, and I was searching for China airborne exposure levels, and not a lot comes out of China, but that was a broadcast from the U.S. Embassy, so I did find that online. You can go back and find that. My data was from July or something. I don't know what it is right now.
Okay. Another question, how does the limit of detection of the photometer compare to that of a gravimetric lab sample or lab method, and specifically for crystalline silica?
Okay, I don't have all the stats in front of me. So the dust track can see particles down to 0.01 microns, so or 100 nano. Let's see, 100 micrograms, so 0.01. I'm confused myself. It's the limited detection. You could probably get a lower limited detection gravimetrically if you do a longer sample. So the more aerosol you collect, the more air you sampled, your limited detection gets lower and lower and lower the longer your samples run. So if you were to run it for 3 days, you can get very low. For silica, it is in the range of what you need to look for the PEL. It is accurate enough to get that at those PEL levels. I don't have the numbers right in front of me here. I'm sorry about that. I could. We do have the spec sheets are on our website. You can get to, and it does have those limits of the sensitivity limits there.
Okay. Another question: are there any field sample data available to study, to review and compare with the real-time sample data for the model for the 8534?
So I don't have any. We have some application notes, but I don't have a lot of data. I have some individual data I've just kind of collected over time. But we don't have a lot of published data on our website. There have been a lot of studies done, and a lot of aerosol studies you see. Some of them have used, people have used our equipment over the years, so there's some things you can find. We do have an app note that kind of lists or summarizes several research papers have been done in the recent past, which has used dust tracks. So I could refer to that as an application on our website. If it's specific to like a calibration factor, we have just examples in a manual for like program medium 510, but they're not intended to be the real cal factor because the aerosol can be so varied. Someone's silica cal factor in Wisconsin may be different than someone's silica cal factor in Maine based on the percentage of silica in the rock. So we don't have a lot of those custom cal factors established for different aerosols just because the aerosols can vary so much.
And we did get a comment along those lines. Someone said to provide accuracy for a data set, I do a retrospective calibration adjustment for each optical data set based on the filter collected for that data. This only works for the size of the dust you collect. So if you're interested in respirable dust, you'd want to use a cyclone to resect the dust being measured.
Yeah, that's a great point. So if you're using an inlet conditioner for size fraction on the dust track, use the same inlet conditioner for size fraction on the gravimetric and vice versa, so you're collecting the same thing. And that's, if you're using a photometer on a regular basis to take measurements, eventually those readings will start to, if they increase, you're probably going to want to come back with a gravimetric measurement and verify, hey, is that approaching the PEL or some level of concern, or is it just a nuisance dust, some kind of background aerosol that's, can you still hear me?
Yeah, I can. I lost you there for a second.
Okay. All right.
Someone was just asking about getting a copy of the slides. Would that be available to them?
I don't right now. It just came to my attention right before I did the presentation that I've used some photos right off the internet. I don't have copyright access to those right now, so let me clean them up. And I guess if you want to email Tom, I can get a sanitized version out to you with just the data and the notes and take the pictures out that are of concern. So if you can get a list of Tom, then I can share this with you.
Okay. Yeah, and I can follow up with the individual that asked about it.
Yep.
So I'm not seeing any more questions, but we had a lot of good ones, so we thank everyone's participation. Again, my name's Tom with RACO, and thank Scott very much for his time. Again, we'll have a recording of this available at our website, raco.com, on our training page. Probably give us a few days, and we'll have that posted. If you have any questions, you can give us a call or you can give me an email at tom@raco.com. And again, thanks again for your time. And Scott, do you have anything else?
No, I'm good. Thanks for the opportunity.
All right, great. Well, thanks everybody, and have a great afternoon. Have a great holiday weekend. Take care.
Thanks. Have a good day.